Hello, and welcome to another E2 tutorial, our programming session. In this session, we're going to look at comparing three or more population proportions and analyzing the data using R. Proportions are basically just ratios, where we take the ratio of a sample out of the main population. Sometimes it could be expressed in percentages or decimal places. So in today's our E2 tutorial, our video, we're going to look at a manufacturing problem. So we have the problem statement, which you can see on the screen. Benton Manufacturing is considering ordering electronic components from three different suppliers. The suppliers may differ in terms of quality, in that the proportion or percentage of defective components may differ among the suppliers. To evaluate the proportion of defective components for the suppliers, Benson has requested a sample shipment of 500 components. So in this case, N, which is our sample size, is 500 from each of those suppliers. The number of defective components and the number of good components found in each shipment are summarized below. So you could see that summary here in this table, right? So we have the suppliers, three of them, A, B, and C, and the component based on the quality, is it defective or good? We could see the number of components that are defective for each of the suppliers. We could also see the good ones from each of the suppliers. Just looking at this, we could see that supplier A has a relatively low defective component, as well as supplier B. But supplier C has a very high number of components that are defective. We often see this a lot in manufacturing, right? Whereby, maybe there's loss of attention or loss on focus on detail, right? And some of these products, or for whatever reason, as they are made, something happens along the manufacturing line. The product is still finished, but the quality does not meet the manufacturer's specification, especially when you're looking at third-party suppliers, right? So in this case, we can see that supplier C has a lot of electronic components that are defective. That's definitely not good for business, right? And also, whatever these components are going to be put into for the final product, you don't want to give your final consumers a product that has a lot of quality issues and defects in them. That would often lead to high returns, right? Because when I get that product and it's not functioning properly the way I want it to function, I'm gonna have to return it, right? Or maybe I get the product and the quality is not what I'm expecting. I will have to return it. So here we get to do that analysis and try to help Benson Manufacturing determine which of these suppliers should they consider doing business with. Now, here are the questions that we have to look at. The first is to formulate the hypothesis that can be used to test for equal proportions of defective components provided by the three suppliers. So basically, we want to see if the number of defective components are equal across all three suppliers, right? And then the second question is to conduct the hypothesis testing, get our p-value, and come up with our conclusion. And then finally, we have to conduct a multiple comparison test between those suppliers to find out which ones are good, which ones are bad, right? To determine if there's an overall best supplier or if one supplier can be eliminated because of poor quality, right? So remember, I said in this electronics or in manufacturing, quality is very important, right? And that is one thing that would help you determine which supplier to go with because you do not want to send the products to your final consumer and they are not happy with the quality of the product. So let's get started with the analysis. So I have my R Studio all opened up. So this is the Benson Manufacturing um, electronic component supplier quality comparison. So the first thing I would do here, as we get started, is to load my R packages. So my step one is to load the R packages. Please make sure you're following along with me as we, as we go through this entire code. Oh, I just remembered, something I forgot to mention. This data set, or the Excel file for this data set, will be linked in the description of this YouTube video, right? So please go to the description of this YouTube video and download this data set into your computer, because we would need it, or we would need to import it into R. I already have it downloaded. Um, so just go there, click on that link. It's going to take you to my GitHub page, and you can download the data set so you can code along with us. All right, so we basically just need only two packages. The first is the read Excel package, which would help us to import Excel files, and the second one is the ggplot package, which would help us in creating visualizations and all of those different things. You can see some of that explanation here as well. So click on that. Do not forget to run them. So you could see once you run them, that's it there. So if you're using a MacBook, you could just click on that particular line and do command and return. It would run it, or just click on run here. If you're using the Windows, I think control and enter should run each line of your code. So our second step, step two, is to import the data into R. Right, so say data. So this is where we call the read Excel function. Okay, so I'm just gonna run this. Right. So basically, you can see our data set here. It has been loaded in the global environment. So the global environment is where you would always get to see the data. So if I click on this, we can see all of that data, right? Starting with the defective for supplier A, for B, for C, and then the good ones as well, right? So I'll close this for now. And then if I run the next line, line 11, it just kind of gives me just a snapshot, right, of the first 10 rows of the data, which also gives me an idea on whatever we're doing. So our next step, step 3, is to create a cross tabulation, right? So we say compute the cross, oh, I forgot how to spell tabulation, the data, right? So we'll just say cross tab, and we use the function table. Then we call the data component. So what we're doing is we're calling this first column, right? Remember, overall, the data has two major columns, which is component and supplier. And then in supplier, it's split into three categories because we have three different suppliers. So the first thing is we call the component, and then the second one will be the supplier, right? So that's what I'm doing here, calling the component first, and then the supplier. All right, so if I run this code, that's line 14, and then line 15. So you can see it exactly the same way we have it here in our data, right? 15, 20, 40, right? 15, 20, 40, and the good ones as well. All right, so we're basically done with this, right, in terms of loading and setting up the table. So the next thing we want to do is to answer the very first question. And our first question here says to formulate the hypothesis that can be used to test for equal proportions of defective components provided by the three suppliers. So we need to first define all of our population parameters and then set up the hypothesis. Now, I think I mentioned this earlier in the video. So we're testing for equal proportions. So basically HO will be that all the population proportions are equal, right? And HA will be the reverse of that. Not all the population proportions based on the suppliers are equal, right? So let's go ahead and do that. So yeah, question one. So so P1. So that is proportion of defective components from supplier A, because remember we're looking just at the defective components. We could also do an analysis on the good components too, right? So, and then we'll make this C, right? So forward null would be HO. So P1 equal to P2 equal to P3. And then HA will be P1 not equal to P2, not equal to P3, right? So that's basically how we answer question one. So we're done with it. So now we can proceed to question two. So question two is asking us to conduct the hypothesis test, right? You can see there, conduct the hypothesis test. Your alpha is 0.05, find the p-value, and then what is your business conclusion? So we're going to do that. So we say, so for three or more population proportions, we're basically using the chi-square test, right? And that's what I've defined as chi-test, right? Just kind of abbreviation for chi-square test. And the function is this. So the chi-square test, and all you just put in there is your X tab, which we created in line 14, right? So please take note of that. The X tab, which we created in line 14, that's all we need, right? So if we run this, boom, we get our result. Everybody's excited. So you can see that Pearson's chi-square test there. You could see your test statistics, which is 14.74. You could see your degree of freedom, which is 2. So the equation for degree of freedom is basically n minus 1, or in some places or some textbooks would say k minus 1. Basically, what k means is the number of population parameters you have, right? So in this case, we have three suppliers, suppliers A, B, C. So our n or k will be 3. You subtract that from 1, that's how you get 2. And then our p-value is 0.000, right? Which is obviously less than 0.05. So let's go ahead and write out our business interpretation. Okay, so because the p-value is less than alpha, we do reject the null, and that means that this is false and this here is true, right? Which we can proceed and conclude that the three suppliers do not provide equal proportions of defective components, right? And if you go back to our result, you could see it here, right? The the proportion or the number of defective components across the three suppliers are not the same, right? Supplier A has 15, supplier B has 20, supplier C has 40, right? And C has the highest while A has the lowest. B is kind of like in the middle, right, of both A and C, right? So our chi-square test is coming out to let us know, hey, the proportions of defective components is not the same across the board, right? This then leads us into question 3 because we need to find out which suppliers are the best, which one has the poor quality. We can kind of hypothesize that C has the worst quality because of the number of defective components, right? 40. But we want the data to kind of speak for itself, and we'll do the analysis to make sure that whatever we're hypothesizing is actually correct. So let's go ahead and look at question 3, right? Which is to perform the multiple comparison test, right? That's what, so conduct a multiple comparison test to determine if there's an overall best supplier or if one supplier can be eliminated because of poor quality, right? Now, the equation we would need to do this multiple comparison test is called the Marascuilo procedure, right? So let me just write it out here. Um, right. So that's what um the equation is called Marascuilo procedure. And what I have here are basically the three-step process to performing this Marascuilo procedure. The first is to find the critical value, right? Which is denoted as CVIJ, right? And I and J basically alternates between the first proportion, right? Which is P1 and then P2, P1 and P3, P2 and P3, right? That's how your I and J would basically alternate. So it's the square root of your chi-square critical, which you get from your distribution table based on the degree of freedom, k or n minus 1. Then, depending on what proportion you're looking at or what supplier you're looking at, you would have it as that sample proportion bracket 1 minus the sample proportion divided by the sample size, and then the other proportion as well. The second is to then compute or compare the absolute difference, right? Which you have as this. So you take the difference between two of them. It has to be absolute, right? So if you get, because of that absolute, if you get a negative, it becomes a positive. And then finally, you compare that absolute value with the critical value to determine if it is statistically significant. So I will walk us through this entire process, right? If for any reason you don't understand something, or you run into an issue as you're coding this, please, you could leave a comment, right? And I'll basically, go in there to the comment section and make sure that I provide you with an answer as quickly as possible. Okay, so the first thing we do want to do here, or I want to do, is to try to compute all of the proportions, right? So basically P1, P2, P3, all of the sample proportions. So when I say proportions, I mean sample proportions, right? First of all, our N is 500. We already established that fact. And our X, which is our sample of interest, in this case is the defective for each of the suppliers, right? So we're going to, calculate all of those different things. So I could just say that P1 is equal to, we could say, okay, let's do it this way. So let's define so X1 is 15, right? So uh, N1 is 500. I could use the same N for all of them, right? Because they all have the same sample size of 500. But if you're doing a problem and they don't have the same sample size, then you need to define, I'll take out this one, then you need to define individual n's for all of them. But in this case, I have the same sample size all through, because if you add up all of this, 485 plus 15 is 500, this is 500, this is 500, right? So that allows me to use one n. But if yours is not giving you the same stuff, then please add it up. So I'm going to change this. If I decide to use n for all of them, I will change this and just say total sample of each component from each supplier, right? That's what I would just do. So I can use the same n all through. Then my x2 will be 20, which is, so that's supplier B. Then x3 is what, 40? Okay, so that's C, right? Then my proportion, right? So P1 will be x1 divided by n, right? So this would be proportion of defective components for supplier A, right? Then P2 will be x2 divided by n. So I could just take this, put it there, change to B, and then P3 will be x3 divided by n. So this would be C, right? So let's run this. Right, so you could see all of our proportions here, right? It's 0.03, 0.04, 0.08. So we'll need all of these numbers when we start doing the comparison. So now let's get into that Marascuilo procedure in terms of the comparison. So we'll just create a new table called comparisons, and we use the data.frame to create that new table. And we want it to have, or before I do this, let me just explain one more thing. So the comparisons, we're doing it A versus B, right? So we're comparing supplier A against B, then A versus C, and then B versus C, right? That's the comparison. So that's the comparisons between the suppliers, right? So now we can proceed with saying that, creating that table using the data frame function, right? So our group one would basically be all of these first ones here, right? So A, and B will be in our group one, right? Because we're starting with comparing them against group two. So we'd call all of this part here. So this, and this is our group one. Then this, and this is our group two, right? So, and then in order to make sure that everything comes out in the table, we use the C, then we'll just say A, then A, and then B. So then group two is B, C, C. All right. So now the next thing we want to do is to list out all of our sample proportions, right? So what are the sample proportion? What was the sample proportion for A, and what is the sample proportion for B, right? So the way it is here, would have to write A twice and then B once. So that's our P underscore I. So what we're trying to do is to then calculate this, like calculate what PI will be, right? We've already done that. in line number 39, 40, and 41, right? So all we just have to do is, so P1 was for A, P1 again was for A, and P2 was for supplier B. So we just write all of that out there. So this is C. So A was 0.03, 0.03, and then B is 0.04, right? Then PJ, so B is what? 0.04, and then C is 0.08, 0.08, right? So, and then finally, our sample sizes for both of them, just 500 all through. Okay, so now we're done, and we could run this line of code. So you could see here, it gives us a table called comparison, right? So if I click on it, you can see our groups because we're comparing A and B, A and C, B and C, right? That's basically what, we converted this here, line 44 to 46, into this, right? So that's what that group one and group two helps us to basically do, right? We can call it a different name if you don't want to call it group one and group two, right? We call it whatever name um, we want. And then the um, the sample proportion for A is 0.03. The sample proportion for B is 0.04, and so on and so forth, right? And then these are their respective sample sizes, right? So the next thing we want to calculate now is we want to use this equation. We want to bring this equation into play. But before we do that, we need to calculate our critical value here. This critical value is very important. So we need to calculate that separately. So define the chi-square value. Remember, our degree of freedom was 2 and alpha is 0.05. So we use this function, right, which basically gives us the um, the critical chi-square value. It's very similar to looking at it from your chi-square table, right? But this function just makes it so easy for us. So our degree of freedom, our alpha, which is 0.05, degree of freedom, which is 2, and then the lower tail, which will be false. So if we run this, our chi-square critical is 5.99, right? So that is good. So let's now compute our critical value for ij. That's this one. The good thing about using R was that if you were doing this manually, because the proportions change, you will have to calculate this for multiple times, right? Because you have three different proportions. But since we're using R and we're basically just having it as I and J, remember we had it here as PI, PJ, NI, NJ, right? R would just basically be the one to do the substitutions for us and get us all of the critical values. So you would basically see it would have three different critical values, which we would use for our comparisons, right? So let's go ahead and calculate that. Compute the CV. So we would say we're just going to create a new column. So we'll call it CV underscore IJ. So the square root, which we had in that equation, the chi critical, multiply that by the comparisons of the PI, multiplied by 1 minus comparisons of PI, right? And then divided by comparisons of NI. So basically what I've just done is to write just this first part of the equation here, this first part, all the PI, right? Now the next one will be the PJ, right? And we should be done. So this is plus comparisons of PJ divided by 1 minus comparisons PJ divided by comparisons NJ. All right, sweet. So we're done there. So if I run this, you would see that if I go back to our table, it has increased. So now we now have the critical values for IMJ. Can you see that we have 3 different critical values because these numbers are different, right? So it's going to give us 3 different. So if we're doing this by hand, that means you have to calculate this 3 times. But with R, it just makes the work so easy because one code takes care of that iterative process for us, right? So the next thing is to compute the differences, right? So when I say compute the differences, what I mean is we're just finding the difference between 0.03 and 0.04, 0.03 and 0.08, 0.04 and 0.08, right? That's basically what I mean by the difference. And remember, it's the absolute difference, right? That's what so maybe I should put it here. The absolute difference, right? So this would be, we create another column called differences, right, in our comparison table. And then ABS is basically stands for absolute. And then the comparisons between PI minus PJ, right? Very stress-free. I love it. Trust me on that one. I love it. So you can see that differences 0.03, 0.04, it gives you 0.01. That's the absolute difference, and so on. But then just looking at this difference, right, you could see that when you compare A and B, the difference, right, in their defective parts is so small. It's 0.01. But just look at the difference between A and C, B and C. It's so large, which is letting us know that C is like a no-no, right? Um, but let's kind of finish up so we can really confirm it, right? So the next thing we want to do is to compute. So yeah, so the final thing is to do step 3, right? Which is to do that comparison between our absolute difference and the critical value, right? So let's say, so this shouldn't be compute, this should be compare the differences with CVIJ. So we'll create another column in our comparison table. We would call it significant, and we'll use the if else function because what we're saying is that if so let me go back to the table. So what we're saying is that if this difference is greater than this, then it should be no, right? If it is not greater, then it would be yes, something like that. That's what the if else function um is basically doing, right? So if else, so we say the comparison, which is the difference, is greater than comparison for CVIJ, then we put the yes or no. So I'll run this, right? And then finally, print the result. So we just say print. We just want to print the entire table at the end of the day. And then I'll run this. Okay, so we could see that table, right? What we're saying now is if the difference, right, is greater than CVIJ, right, you should put no. So you can see that that is not greater, right? But for the other one, the difference is actually greater. So with this, we can come up with our final business conclusion based off this. So business interpretation. So supplier A and B are both, which we can basically see, right? The difference. It's so small for A and B, but it's so large for B and C, right? So there's that statistically significant difference between all of them. Now we can then proceed to say, yeah. So obviously, nobody will want to buy a product from a supplier who has poor quality, right? So in this case, when we go back to our crosstab, right, or not even our crosstab, let's look at the proportion we calculated here, right? You can see that supplier C has 8%, right? Which is 40 electric components are defective, which results in that 8%, right? It's too much. So our question was asking us, you know, if one supplier can be eliminated because of poor quality. Obviously, that will be supplier C because they have the higher proportion of defective components. Then finally, okay, so basically, when you look at the proportion of defective components between supplier A and B, you can see it's just like 3% and 4%, right? So since they don't have that very high um, proportion of defective components, Benson Manufacturing can still consider them as good candidates to supply this electrical components that they are looking for, right? So in that sense, we've basically looked at this manufacturing problem and used it to solve or analyze a data on comparing three or more population proportions. I hope this was helpful to you, right? Please, if you encounter any challenges whatsoever while doing this code, please put your questions in the comment box below the YouTube video. I would do my best to respond to you. And also, if you haven't liked and subscribed to this video, please do like and subscribe and basically, share this channel with your friends who want to learn about statistics or who want to learn about our programming. Thank you so much for watching this video and see you next time.